Hi everyone, and this is going to be a short video going through tolerance determination for your technical sketching portfolio. So originally we were going to have this as two videos, one on linear tolerance determination and then another on geometric tolerance determination. But because they kind of go hand in hand, what we've decided to do is combine these two together. So for your technical sketching portfolio this week, there's only going to be two videos rather than three. So what is tolerance determination? So essentially linear tolerancing is concerned with the sizing of dimensions. So essentially giving it plus or minus values. However, linear tolerancing takes no account for errors that may take place in the geometric shape or form of the elements that you're actually trying to machine. So clicking on the screen through here. So for example, if we consider a shaft as we have with the GIF on the screen through here, which may be in tolerance as the diameter dimension with our plus minus values is concerned, it may be useless if it is not acceptably straight within its length. So what are we actually talking about here? So if you imagine that the central section of the shaft is essentially bent out of shape. So if this is bent out of shape, and you can see, and what we're showing this with is a little what we call a dial indicator. You can see that we've got the bentness in the shaft, if you like, with this little needle moving. So what that's indicating is that the shaft isn't true, if you like, so it isn't perfectly straight. And this could lead to errors when actually assembling the components together. So when we consider linear tolerances, we also need to consider geometric tolerances to make sure that the item's actually going to work the way that we intend it to. Okay, so let's jump forward into geometric tolerances. So you should be fairly comfortable with some of the stuff we've been working through in the course. What a linear tolerances is essentially our plus minus values, and you're going to learn a bit more about how to determine those more accurately in future courses. Again, we're just introducing these concepts at a high level, so you're aware that they exist, and when you work through them further in future courses, you know what they are. So let's work forward into geometric tolerances. And again, we're going to keep this at a fairly high level. So there's a whole bunch of different types of geometric tolerances. So some things might be when you're talking about planar surfaces, such as things being in a flatness to each other, straightness or squareness. Other things could be having common datum planes, for example, so things are positionally geometric tolerance relative to each other or in a parallelism, for example. Roundness or circularity, components being cylindrical to each other, angularity, concentricity, or symmetry as well. So these are some of the terms when we talk about geometric tolerances that you may want to use. And you can implement these in Creo as well, where there's some videos on that for you to work through as well in the course. So if we use the example of the little video that we've got on the screen through here, so if we look at our little red plate, if we look at those two little sort of cylindrical spigoted sections, if you like, so welded on sections, if they weren't cylindrical about each other and perfectly squared to that bottom plate from a geometric tolerance point of view, the red plate on top would not be able to slot on. And in a similar fashion, if we didn't have a geometric tolerance for the holes, or we didn't have a sufficient linear tolerance large enough where the holes were either a little bit too tight or they were a little bit out of square, the plate wouldn't be able to drop on as well. So this is why linear and geometric tolerances work hand in hand. Okay, so let's jump into some examples of how to do tolerance determination. So what we're going to use firstly is the TSP shaft example, and then we'll work through the other example as well. So what we're expecting you to do for the shaft example in your TSP this week is to identify one geometric tolerance, two keyway tolerances, and also a bearing tolerance. So the keyway tolerances, that's something that we've worked through a little bit previously in the course, and for the Creo portfolio this week as well, I've gone through a bit of a more of a detailed example of how to determine and implement those onto a drawing within Creo. So I'd recommend going to watch that video if you're not quite sure of how to determine those particular tolerances. For the bearing tolerance, this is already stipulated. I've already selected this according to some standards, so the ISO 286 standard for the specified fit that the bearing manufacturer specifies. So the process to actually determine these particular tolerances, that's something you'll learn in some future courses. Again, we want to keep this at a fairly high level and teach you how to actually implement these onto drawings, and then the determination of specifying those tolerance and fits, that'll come into some future courses, so don't stress too much about it at the moment. So if I go to and bring over my technology through here, so this is using my Remarkable. So what we essentially have, and sorry, just before we jump into that, so for our bearing tolerances, it's essentially for our 25 mil thicker section of the shaft through here, we're going to have an upper bound of 0.035 millimeters and a lower bound of 0.022. So essentially what it needs to be for the shaft, it needs to be slightly bigger in both cases because the bearing's going to be spot on to the 25 millimeters. So if I bring the Remarkable, click that there. So what the actual notation on your drawing will be, if we go to our diameter symbol, 25 millimeters, and then it's going to be plus 0.035 and then plus 0.022. So essentially what this means is, for a fixed dimension, what the machinist would be shooting for is 25.022 or 25.035. Anything between those, they've nailed what you've basically stipulated that the tolerance needs to be. So that's how I would be implementing, and obviously you would have the central section showing the shaft something. If we imagine our shaft like that, for example, and the top section there, dimension would look something along those lines. Okay, so if I just minimize that for a second. So it should be able to hopefully work through the bearing tolerance reasonably as a reasonably straightforward process. As I mentioned before, the keyway tolerances, that's something I have worked through in the particular other example video. The one that I do want to spend a little bit of time on is the actual geometric tolerance. So what are we talking about here in the geometric tolerance? So if we consider this shaft, for example, we've got a bearing in the middle and two fixed sections either end. If we assume that the two sections either end are perfectly square and where they need to be, and then we get a slight bit of out of true, if you like, or the central section of the shaft is a little bit bent, we need to stipulate a geometric tolerance to make sure it's within a bound where it's going to be straight enough to where we need to be. So the way that we interpret this is the axis of the central portion must be contained within a cylinder of diameter 0.05 coaxial with the common datum axis. So essentially what this means is, if we consider both ends to be our common datum axis, the central section can only be within a 0.05 millimeter diameter cylinder out of true, if you like. And I'm going to draw an over-exaggerated example of this shortly. So the way that we actually implement this on drawings is, you'll have your common datum B and your common datum A either end, and then that central section is where we actually put the geometric tolerance. So bringing the remarkable back up. So I'm just going to bin all of that stuff that I've previously done. And probably a neater way to do it is to cancel it like that, and we just get rid of it like that. Okay, so now what we're going to do is I'm essentially going to draw an over-exaggerated version of this shaft. So if we consider our two end sections, something along these lines through here, okay, and then if we put our common center line through the guts of all of it, and then the way that we draw that onto a drawing is we have our little triangular section with datum A, and then we have our little section through there with datum B. Okay, so on the drawing, the way that you actually, so I'm going to do this in two ways. I'm going to draw how you would actually draw it on the drawing for your geometric tolerance. So we come through to there, drop that down, and come across there. Oh, apologies for bumping. So the way that we actually draw this particular datum, our notation to show that our geometric tolerance. So in this case, our symbol is like that. We've got our box, it's diameter 0.05, and then it's A-B. Close all that off. And that's how we actually implement that geometric tolerance. Let's step it down a little bit further now though. So I'm just going to change colors, and let's go to a red. So what does this actually mean in practice? So if we consider this diameter 0.05, and I'm going to over exaggerate this here and bend it downwards. So effectively what that could mean is our shaft may be effectively bent out of shape this way. So if we consider our center line running through something like that, effectively what it's saying at its worst point, the dimension between there where I've got my little question mark, the biggest that can be from the stipulated geometric tolerance that we've specified is diameter 0.05. And that's in reference to either end, where we've referenced those datum planes of A and B. So if we come back to the particular drawing just as a bit of a rehash, so you need to do a hand sketch of this in third angle projection. You're probably going to want to use a section view because it's going to make your keyway tolerancing a little bit easier. So we're expecting a geometric tolerance very similar to what I've just drawn on my Remarkable on the just a couple of seconds ago. We're expecting two keyway tolerances, one for the width, one for the depth, and then that bearing tolerance as we ran through shortly a little bit ago. So hopefully in terms of the shaft example, that should hopefully be pretty straightforward. And as I mentioned, don't get too stressed about the values you're actually using. We're here to help you determine those at the moment. You will learn a bit more about how to determine those more accurately in future courses. Not expecting you to know that for this particular course. Just want you to know how to implement those particular tolerances on drawings. Okay, so jumping forward into the next example now. So for the tolerance determination, the TSP mounting plate, so the hub example is essentially what we're looking at here. So what we're expecting you to do here is have a geometric tolerance, which we'll run through shortly, and a bearing tolerance. So again, I've already stipulated this for you out of the ISO 286 standard, so for the class of fit that's been specified by the bearing manufacturer. This time what it's going to be is, because of the pressures acting on the bearing, you're actually going to be under. So if I just go back to for the particular example that you're looking at, it's going to be diameter 47 minus 0.021 of a millimeter and then minus 0.037 of a millimeter. So I won't go through and actually draw that on the Remarkable. I'll basically assume that from the first particular example that we had, that you'll be able to work through that particular example. So just to recap, if I jump back, so we went through before with the diameter 25 plus 0.035 and then directly underneath it for the tolerance plus 0.022. So in this case, what we'd be looking at is diameter 47 minus 0.021 and then directly under it minus 0.037 for your tolerances. So in terms of the actual geometric tolerance, what we're going to expect you to have, so the three holes around a common datum of this central hole. So what we have here is, we've got essentially, in this example that we've got here, this is more of a positional planar type geometric tolerance that you're considering this time. So what we have is, if we consider the center hole of this central hole as our common datum plane, which is shown by the A through here. So you would do the same essentially for this central hole on the diameter 100 with an A datum. Each of these holes, if you imagine from a positional sort of cylindrical coordinate, it needs to be within 0.1 of a millimeter in reference to datum plane A. So all you would simply need to do for this example, for your holes up here, for example, you would just need to whack in something similar to this underneath that when you do your hand sketch, obviously with all the dimensions and the like on it, and you're going to use that central hole as that A datum plane. So this is where you can actually use the same, so we're using both the positional for both the cylindrical and planar coordinates here. What you could also do, if you went back to your previous example, you could use a coaxial geometric tolerance, which is essentially two circles in each other. But I'm quite happy for you to use the positional for both. As I've mentioned a few times, geometric tolerancing, we want to keep this at a fairly high level, just so you know they exist and how to add them to drawings and about the datum planes and the like and the plus minus values. The actual determination of how these work in practice is something you'll do in some future courses, so don't stress too much. So hopefully this video has been useful in terms of how tolerance determination works and how you implement them onto drawings. If you do have any questions, please certainly do reach out during one of the computer lab sessions, where I'll be more than happy to have a chat about it. So looking forward to watching everyone get the tolerance determination done for both the technical sketching and your Creo portfolios this week. If you do have any questions, please certainly do reach out, and we'll catch you in the next video. Thanks for listening.